let me show a very simple example, just to remind you of a geometry which is not the geometry of Euclid, in which the proposition that every triangle is 180 degrees simply does not hold. And it's a familiar and an easy geometry, which we know all the time. Imagine this balloon to be a sphere. I will work on part of it only. It will be rather spherical. If I draw a small triangle, I think you will believe that nearby, if I look at it closely, it is very near a flat surface, and my propositions will not be much different if I work on the flat surface. But if I draw a large triangle, a line like that, and let me draw a nice right angle here. It's a good right angle. And a nice right angle here. That's a good right angle. But if I continue with straight lines, of course, on the flat plane I never meet. But here I make a splendid triangle. Well, I submit, if they're 90 degrees here pretty close and 90 degrees here pretty close, I've used up the 180. There must be something to assign to that triangle. Of course, you know very well the theorems of Euclid simply do not apply in the non-Euclidean geometry of a sphere. And what determines whether they apply or not, how closely they are approximated, is one thing and one thing alone. Namely, is the triangle large or small? And when I say large or small, I say with respect to what? And of course the answer is quite clear: large or small with respect to the sphere. If they are tiny triangles, as we draw triangles compared to the great globe of the Earth, then Euclidean geometry works. If they are huge triangles, like the triangles made on the sphere by the lines of longitude and latitude, then Euclidean geometry is no longer true.